Well, hello everybody, and welcome to Chem, and we are starting a new unit, and this unit is about thermochemistry, right here, thermochemistry. And we've learned a little bit about thermochemistry, as you will see in a sec, but let us start off with this question. Consider the reaction of hydrogen and oxygen, in which I have a negative 480 3.6 kilojoules. That's a negative value, so we know it's exothermic and that energy is released. And the question is this a reaction, something one would study in thermochemistry, right? And so what we want to do really is understand a little about thermochemistry. Cool, thermochemistry. And you know I love definitions, and so let's go with this definition. What is thermochemistry? It is a branch of thermodynamics. Thermodynamics. You're going to have to wait a while to learn what that word means because I don't want to describe it yet. Branch of thermodynamics focusing on what? The relationship. Yikes, this is becoming a long definition, isn't it? Focusing on the relationship between chemical reactions, okay, we know what that is, and energy changes involving heat. Oops, involving heat. There we go. Okay, it's a branch of thermodynamics focusing on the relationship between chemical reactions and energy changes involving heat. Okay, now that is a definition that's worthy of being known, but you know what? Just for our purposes, just to understand, really, thermochemistry is about one thing, and the answer is it is about heat. That's really, to boil this definition down, and no pun intended, boil, haha, we want to deal with heat. That's what we're talking about. What happens to heat in reactions, either exothermic or endothermic, right? Good. And we did learn something already about it, right? We learned a little bit about what heat is. We learned in a previous unit that heat is what? It's the transfer of energy between objects of different temp, right? Different temp. Cool. And we learned some equations, right? We said, hey, Q equals mc sub p delta T, where that is Q is my heat, and this is my specific heat. Specific heat. And we learned what else? We learned some things about phase changes, and that in a phase change, Q is different. Q is equal to usually moles or mass times a latent heat of something, right? And we learned how to do energy diagrams, correct? Not energy diagrams, heating curves. Sorry, there we go. So you already know something about heat, and so we're just going to go in more detail in this unit. So back to our question. Is this reaction something one would study? Hey, in thermodynamics, we have a reaction and we have heat, and so whenever we have heat and we have a reaction, then that is certainly, thermochemistry. Yes, this is something we would study. Okay, so now the question is, we have 483.6 kilojoules, right? We said it's a negative value, and so we said, oh, that's an exothermic reaction, and the question is, where did that heat go? Well, let's go back and add some more things here to our discussion. And really, one of the underlying topics, not topics, but concepts that is behind thermochemistry is something we call the first law of thermodynamics. Thermodynamics. Cool, right? And this sounds scary, but it's really a piece of cake. Here's the first law, and you really know it. It's just that we haven't expressed it as the first law before, and that is the energy of the universe is constant. Hey, that's an easy thing, right? It's bad news for everybody who wants more energy, that, oh, we just need to have solar or wind and we can use all the energy we want. No, unfortunately, the energy of the universe is constant. You are not going to create energy. Another way to state this is what? Energy is conserved, or energy is neither created nor destroyed in any process. Okay, so that's really the first law of thermodynamics, meaning, hey, if I so-call have a positive heat somewhere, that means that must be a negative heat somewhere else. And back to our question here, first question, where did this 483.6 kilojoules go? Okay, if we believe in the first law, it doesn't magically appear and it doesn't magically disappear. It just means it's being transferred from one place to another. And that brings us to another concept that we want to talk about here with thermo. Let's go with the blue. Zoink. Oops, look at that dead end. Ooh, go over here. Na 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 na. And we want to come down here and we want to talk about the concept of the system and the surroundings. Okay. And when you're talking about energy, you really need a perspective. So everything is relative and there talks about energy. And so you need a point of reference. And so in chemistry and also in physics, we talk about the system and the surroundings. And what is the system? The system, it's quite simply the part of the universe we are investigating. And that can change every day. If we're looking at a reaction, then it's probably the reaction. If I'm looking at the room, then it's the room. But I can define essentially what the system is. And then the surroundings are, what are the surroundings? Everything in the universe. Boy, I like that. Everything in the universe except what? Except the system. Cool. And so we might as well put this here. We can do this algebraically or mathematically, right? The universe is composed of what? The system and the surroundings. So if I have 2H2 plus O2 going to 2H2O, and I'm looking at that reaction, then I would call this the system. And everything else, the whole rest of the world, the whole rest of the universe, yeah, the billions and billions and billions and billions of stars are what? The surroundings. So everything outside of my reaction is the surroundings, the way I define it. And what's kind of cool here is we can define it almost any way we want. You just define something as a system and everything else is the surroundings. And when I add them all up, what do I get? The universe. Ooh, man, that's almost too hard for me to comprehend. Ouch, my brain hurts. So to this question, well, what do we want to say? Let's call this my system. So I said I had my system, and so here's my system, and I have my 2H2 plus O2, and that goes to form 2H2O. And when that happens, what happens? What? Yoink! I spit out 483.6 kilojoules of heat, right? Since it's negative, that means it was lost. It is exothermic. My products have less energy than my reactants. And where did that energy go? It went someplace. It went that way. Where? It went from where? It went where? Where? Well, this is my system, so it went into the surroundings because it doesn't disappear, or else we would violate the first law of thermodynamics. So that just means the rest of the environment, the air around the reaction or the glass that is holding the reaction, the heat went to one of those places or all of those places. Got it? Okay. Really, there's nothing difficult about that, but I did want us to get into it a little bit. Hope I wasn't overly didactic. Here we go. Now let's consider this an apple hanging over Newton's head. Hey, I like this. What type of energy does the apple possess? Okay. Well, I guess where I'm going here is I'd like to back up a little bit and talk just a little bit about energy. So we're going to start a new concept map, and it's not going to be a long one, but we just want to talk about energy. We need to back up energy and make sure we understand, because remember, in thermodynamics, we're looking at chemical reactions and energy changes involving heat. So let's talk a little bit about what energy is. So energy, let's go with our definition. What is energy? It is and you'll get different definitions, but this is the definition I'm going to run with. The capacity to do work, and that's where my physics people often like to stop, and the chemistry people probably will go with this as well, and or produce heat. So that's what we're going to look at as energy, the capacity or ability to do work and or produce heat. Good. And I want to talk about several types. What are our types of energy? Well, you know some of these already. I think we talked a little bit about one, kinetic energy, right? And what is kinetic energy? It is the energy contained in motion, right? The energy of motion. So the energy the capacity to do work or produce heat as that can result from a body in motion. And what is the equation for average kinetic energy? 1/2 mv squared, where v is the velocity. That makes sense, right? What we want to know is I have a body that has a velocity or a momentum, and we want to say, hey, how much energy can I get out of that? And so that would make sense that average kinetic energy is related to velocity of my particles, and m is, of course, the mass, right? Mass. Cool. Now, let's look over here, and another type is what we call potential energy. And what is potential energy? Well, potential energy is the energy based on position. Got it? The energy based on position or, excuse me, composition. Composition. Good. The composition of things is a potential energy as well as the position of things. Now, we have two types of potential energy that I want to talk about. One is positional potential energy. Excuse me for a sec. Okay, I'm back. And positional potential energy, blah, blah, blah. Positional potential energy. And that is the potential energy based on or resulting from the position of objects relative to each other. That's easy, almost silly, right? What is my equation for this? Usually this has to do with gravity, and so we're saying that the positional potential energy is equal to mgh. So that the mass of my object times the gravitational constant times the distance away from the Earth in this case, height, I hope I can spell that right, height is equal to my positional potential energy, but we don't care too much about that. That's a physics thing. The one we really care is what we call electrostatic potential energy. Potential energy. All these polysyllabic words make a challenge for me, don't they? Positional potential energy, not positional, electrostatic. And this is the potential energy arising from charges on particles. You guys know this well, right? Charged particles are either attractive or repulsive. And so if I have a negative and a positive, these guys are attracted to each other. If I have a negative and a negative, they are repulsive to each other. And those represent a form of energy. And that potential there, remember, as I take a negative and a positive and I separate them, that requires energy of me. I put energy into that system, right? That is what we'd call as endothermic, right? When I break a bond, I have to put energy into it. And that is, why is that? Because there is a potential that is related to that positive and negative. Just as I bring a negative and a positive together, what happens? Energy is released because there is a potential energy associated with them being separated. And as I bring them together, my potential energy decreases and energy from them is released. Got it? And what is my equation? And this is a very important equation. Really, the force is more important, but this comes out of Coulomb's law, and you will use it a whole bunch later in life. Electrostatic potential energy is equal to K, Q1, Q2 over R. That is the the electrostatic potential energy. Q1 is the charge on one of the objects, charge on one object. Q2 is the charge on the second object. K is a constant. And R is the distance between my objects. So what this says is what? Hey, if I got two charged particles, the potential energy is inversely proportional to the distance and directly proportional to the charge on each of the each of the objects. So the farther, the closer my, well, we'll just leave it right there. That is my electrostatic potential energy. And next year, this is the big equation you're going to want to learn, is the force between a positive and a negative is equal to K Q1 Q2 over R squared. And this is what we call the Coulomb's law. But I'm getting a little bit ahead of myself. Let's call it quits right here on our discussion of energy, and let's try to figure out what we're talking about here. Okay, so I have an apple hanging over Newton's head. What type of energy does this apple possess? Well, this has to do with what? The position of the apple relative to the head. So we'd call this positional potential energy. Okay, cool, we got that. What is the mathematical expression? Well, the positional potential energy is equal to mgh, that the mass of the apple times the gravitational constant times the distance from the Earth to the apple represents that potential for that apple. Good. You guys do this one. So I have H plus. What is H plus? Hey, that's a proton, right? So I have a proton and a vibrating electron separated by 0.05 angstrom. So just put us an angstrom, it's a measure, and it's just really, really small. That's all you need to know. What type of energy does the electron possess? What is the mathematical expression for this type of energy? Okay, I'll give you a few seconds to think this one through. Well, this is a little tricky. We've really got two types of energy. I have a vibration and I have a positive and a negative, right? So If it's vibrating, that means it has motion. That means I have kinetic energy. But since I have a positive and a negative, I also have what? Electrostatic potential energy. So I have two types of energy in this system, right, that's being represented. And that happens all the time. We rarely have one type of energy only. It's usually all kinds of types. But in this case, we just wanted to focus on two. And they're and if you're a physicist, you might even say there's three, but we're going to let it sit just these two. What is the mathematical expression for each type? Well, my average kinetic energy is equal to 1/2 mv squared, and my electrostatic potential energy is equal to k q1 q2 over r. There we go. Questions? All right, let's see what we have next. Let's see if we can get through work, and then we'll call it a day. I'll tell you what, we'll just call it a day right now. Next time we'll take care of what? We'll take care of work. And yeah, so we'll call it a quits right here. And next time we'll do work. I'll catch you next time. See ya.